Okay, let's continue playing a little bit with these generalized linear models that we were talking about, in particular with the ones that fall underneath what's usually described as a logistic regression. But consistent with what I had said earlier in the semester about regression, ANOVA, ANCOVA, factorial, blah blah. These are all just linear models, and you don't have to necessarily have only one single continuous predictor with a response variable. And we'll stick with playing around with our friend the logit, which is above one of my shoulders. There it is. Almost. See it? There it is. That's the logit. For two reasons. Just first of all, to demonstrate to ourselves that we can set these up as what would classically be called an ANCOVA or an ANOVA or factorial, whatever you want to think about it. But also, more important, to show that there's an alternative way in which we can input the data into R and for it to do the generalized linear model. So if you recall, the last time we had zeros and ones. And that was our response variable, and it was just a bunch of Bernoullis. But as we know, Bernoulli is just a special case of a binomial, because a binomial is just multiple Bernoulli trials. And so what we have the power to do is, for any given response variable, we could say like 3 out of 5 or 7 out of 10 or whatever it might be. And so what we're going to do is we're going to just play with some data, real data actually, where so when I was a youngster, some of my dissertation project when I was back in graduate school was looking at the effect of clutch size in these really handsome butterflies called pipevine swallowtails, and they're toxic. And so I was testing various hypotheses about the effect of group size and the probability of survival. And so I set up a really simple experiment where I simply manipulated clutch size, the number of eggs that were laid together, and I manipulated them between group sizes of 1 and 20 for this particular experiment. I think it was 20. I don't even know. We can look. And what I did is I recorded them through the first 2 developmental stages of being a caterpillar. So they start out really small, like a grain of rice, and then they get like a little bit bigger piece of a grain of rice, but still pretty small when they get to the second instar. And so what I was looking at was how group size, because they feed as groups, they all hatched simultaneously and then they would feed in tight clusters on the leaf, how group size affected the probability of survival. I only did it for early instars for this experiment for logistical reasons. It's really difficult to keep track of them when they start getting older because they start moving around a lot, and also they stop feeding in tight groups when they get larger. So this is something that's unique to the earlier instars. Probably more information than you wanted to know, but what the heck. For me, at least, I don't know when you're watching this. For me, it's 5:58 on a Friday, so cheers. Okay, so we're going to read in this data. And what I did with this particular experiment is, let's take a look at it here. Copy. Let's just put it there. That's what it's called. And so what I did to look at the effect of group size is I put various group sizes out in the field. So this is clutch size, and so like this one had 4, 4, 4, 5, 5, so on and so forth. And I had 2 different treatments. I had what is called a control treatment, which is basically the egg clutches were put on the plant, and I, for the most part, left them alone. The other treatment was exclusion, and that exclusion was the exclusion of crawling predators. What I did is I took this stuff that's called tanglefoot, which is this really gummy, sticky material that prevents ants and other insects from walking around gardens, for example. People sometimes put it underneath bird feeders and bird nests, especially in areas where there's lots of fire ants. And so it's an effective way to exclude crawling predators from the plant. It did not exclude flying predators, so here I'm just looking at one particular predator guild, which is the crawling predators. And you can see I have clutch sizes here ranging from 4 to 17. And in total, I did this 200 plants in this for this data set. And so the difference with what we had done before, where it was just a bunch of Bernoulli trials, what we're going to be able to do in R is we're going to be able to give it both of the binomial outcomes as a response variable. In other words, the response variable in the model is going to be two columns of data that are going to be either successes or failures. And so here we can call successes living and a failure a death. And we can set this up as a generalized linear model to look at the effect of clutch size and treatment and see if there's any interaction between clutch size and treatment. So this sounds a lot like a classic ANCOVA, and that's because it is an ANCOVA, because all an ANCOVA is doing is explaining the experimental design. So let's just call it an ANCOVA design, but we're going to analyze it as a generalized linear model with a binomial error structure using a logit. There it is. A logit link function. Okay, so to make things easier for ourselves, I'm going to just separate out all of these things from that object that I read in. I don't want to deal with the data frame because this is just going to make it easier for our purposes. So I'm going to create something called serve data, which is survival data, and it's going to be a matrix of those first two columns. I have to tell it as matrix because the GLM function in R will only accept a matrix as the response variable. It will not accept a data frame. It'll just give you an error saying it's the inappropriate type of error and it doesn't know what to do. So I'm cutting that error off at the pass, so that way we don't have to worry about that. I'll just turn that off. Okay. So yeah, and then we'll have clutch size and we'll have treatment. So we have all of our data set up. And so we can go ahead and we can start with, let's just make a model, because that's what we love doing, because now that we know that these are all just models, let's make some models. It's going to be a GLM, right, where we're going to say that serve dat is some function of clutch size by treatment, and the family equals binomial. So this is my way to ask R very kindly to use a logit link function and treat this as a binomial error structure. Again, if we look at the serve dat, this is our response variable. Notice that it's two columns, right? And those two columns are either of the possible outcomes of a binomial distribution. So you're either living or you're dead. And so that's what our response variable is. And then we're going to do clutch size by treatment. So let's go ahead and we can do that. We didn't get any errors. That's nice. Let's take a look at the summary of our mod. We want to take a look at the summary of our mod. And why do we want to do that? Because we want to make sure that we don't have this problem where our model is doing a really poor job at predicting our data. And this is where we go back to thinking about the residual deviance. So the null deviance, again, is a model where all you have present is an intercept, whereas the residual deviance is including clutch size and treatment and the interaction as terms in the model, and clearly it's doing a better job because the deviance has gone down. But what we'd like to do is we'd like to test. I can eyeball this, but let's be honest, I'm old and I've been doing this a long time. That 121 or 221 is pretty darn close to 195, so I feel pretty good. But let's go ahead and do it formally by taking the p chi-square, and it's going to be 221.79 with 195 degrees of freedom, and lower tail will equal false. And so from the perspective of statistical hypothesis testing, we run this, and we fail to reject the hypothesis that our data are different. We fail to reject the null hypothesis that our, I guess we just accept the null hypothesis. It's Friday. Basically, it's not significant. That's our p-value. We're happy with our model. That means that our model is actually doing a pretty good job at predicting our data. Okay. And so once we have that, then we can go ahead and we can use this. Actually, let's go back to this deviance for a minute, because this is kind of a fun piece of trivia. You can take 1 minus 279.79 divided by 455.94 And that's going to give us an estimate as to the proportion of the variation in our data that our model is actually explaining. So it's analogous to an R-squared. With generalized linear models, the calculation of the R-squared is a little bit different, and there's actually a lot of different approaches to do it that don't always agree with one another. This is one way to calculate the R-squared. There's actually an R package called library R-squa, and there's a function in that package called R-squa. How about that? And if we were to give it our model, and then we were to say the type of R-squared that we wanted to calculate is KL, and we can look up what that means. RSQ. So this is the help. This is just the help file for the R-squa function. And if we go down to the type, KL here that I've typed in is the KL divergence based. Dun, dun, dun. And I just wanted to run that one because I run that, and it's giving us basically the exact same value as when we did it by hand. The numbers are going to be a little different because the output that I cut and pasted from the summary function only has 2 significant figures. The computer is keeping track of a lot more significant figures. But that's basically how that approach to calculating the R-squared works. The default is actually this variance function based, this newer method, Zhang 2016. So if we had just said R-squa mod, we would have concluded that we're explaining 59% of the variation. And again, that's because it's the default. We would have gotten the same answer. Whoa. If we would have gotten the same answer had we said V. All right, same exact thing. Okay. I'm not gonna advocate one over the other method of calculating the R-squared. You can also use this function to calculate the adjusted R-squared. That's one of the arguments. By default, it just gives you the unadjusted R-squared, but we could, for example, take, we could say adjust ADJ equals true. Okay, and then so that is going to be, that's the adjusted R-squared. And remember that the adjusted R-squared is always going to be lower than the unadjusted R-squared. And again, for thinking about the adjusted R-squared, one way of thinking about the adjusted R-squared is it's our estimate of describing how much variation our model explains about the world out there, as opposed to the unadjusted R-squared is all about how much of the variation is our model explaining of our data at hand. And then also, if you wanted to, you could use that adjusted R-squared for model selection. But again, all the rules are still kind of applying when we think about model selection and stuff like that, and how we interpret things that we did with the general linear model. The only difference here is that by using that GLM function and saying that the family is binomial, that we're doing things using that logit link function so that we can have a binomial error structure. Okay, but we digress. So here we had our model, and we liked our model, and we could go ahead and we could do an ANOVA on that model. Remember the capital ANOVA will do that analysis of deviance for us, which is essentially the chi-squared. Last time we chatted, we did it long and cumbersomely by hand. Now we can just take the shortcut and say ANOVA mod, and what do we got? Well, what we have is a significant interaction term. So just like with the rules that we had with a standard linear model, with a general linear model, what we want to do then is go ahead and let's just split up our model really quickly just to understand what might be driving that pattern. And so what I've done is, because of how the data are arranged, if we go back up to here, this is going to be very convenient for us, not by mistake, I assure you, is that the first 100 values are in the control group and the second 100 values are in the exclusion group. So it's going to be quite easy for us to separate apart the control, which again were the ones where natural enemies were allowed to crawl over the plant, whereas in the exclusion group, those crawling predators were excluded from coming into contact with my caterpillars that I was loving. Talking too much again. Okay. No. So what do we got? So what I've done here then is I've just said that our new clutch for the control group, so I'm calling it clutch C, are just the clutch sizes from 1 to 100. And so there's our clutch sizes from 1 to 100, ranging from 4 to 17. With I'm going to do the same thing with the survival data. And I'm calling it here new. I don't even know why I called it that. Let's just call it. Yeah, I'll just leave it. Oh, because it's new. Of course, yeah. So it's the new survival data. Good work, Jim. For the control group, so it's going to look something like this. Again, we have 2 columns, successes and failures. And then we're going to put that into a general linear model where we are going to basically say, how does clutch size influence the probability of survival? And we're doing that because we're telling it, hey, it's family binomial. These are binomial random variables that we're giving it. So we go ahead and we run that. We can go ahead and we can do the summary. We can still eyeball make sure our model's not blowing up with the dispersion pattern. At this point, you don't really have to worry about the deviance that much, just because we've already settled on our big model that we like. What we're really interested in doing is doing the hypothesis testing on the split apart model so we can understand what exactly is happening. And so I'm going to go ahead and I'll run an ANOVA on that. And what we find is it's significant. And what that means is that clutch should stay in the model for the ones where you're in the control group. So clearly there's something going on with clutch size and survivorship when you're fully exposed to natural enemies. And if we go up here and we look at the parameter estimate, which is 0.3285, if you recall, if we exponentiate that, now we're in units of the odds ratio, right? Because that 0.3285, that was in log odds ratio, because that was all given to us from that logit link function. Now we exponentiate that, and we have it in odds units. And so what that means is that every time you increase clutch size by 1 individual, your probability of survival is going to increase 1.39 times, so roughly 1.4 times. So that's pretty good. It's telling us that clutch size is potentially an important thing determining the survival of caterpillars when they're exposed to natural enemies. And we can go ahead and we can do the exact same thing. Don't need that. Let's see here. So now I'm just looking at the treatment ones, and again, the treatment ones are the ones where the crawling predators were excluded. And I can go ahead and I can run an ANOVA on my mod T for the treatment group. And there we have it. I failed to reject the null hypothesis. And the null hypothesis is that there is no effect whatsoever of clutch size on survivorship. And so what that tells me, and what that told me at the time, is that in the presence of natural enemies, larger clutches will have a higher probability of survival versus smaller clutches. But when you exclude natural enemies, there doesn't appear to be any effect whatsoever of feeding in a large group. And so that was just a simple experimental way to kind of address an adaptive hypothesis about whether or not clutch size is some kind of a defense strategy in this particular group of butterflies. And so what I've included in the code is just an example of a pretty plot so that we can look and see what these all look like and understand what drove that interaction term. So I'm going to go ahead and make things ugly, I guess. And there it is. Look at that. And so the open circles here are the circles that are describing the probability of survival for caterpillars that were exposed to natural enemies. And the black circles are the probability of survival. Describe the probability of survival, this line right here. This is the proportion of individuals that survived in each of those groups. And then these lines show the changing in the probabilities of survivorship. And so clearly at really small clutch sizes, you're not going to do very well compared to if you're at larger clutch sizes. And this is just one kind of graphical way that we can show it. Whereas when natural enemies are excluded, it looks like there really is no effect whatsoever of clutch size. And so, yeah, so that's just an example of the motivation here is to show that there's an alternative way that you can put data into these generalized linear models, but then also just to illustrate that once you understand how the link functions work and what these generalized linear models are doing, with the exception of checking the deviance to make sure that your model is doing a good job at predicting the data, it's really not that different than when we did general linear models. It's just the parameters are interpreted slightly differently because we need to, in this case, we need to exponentiate them and understand that every time you increase clutch size by 1, you will increase the probability of survivorship by 1.4 times. And then, of course, it will ultimately asymptote out because when thinking about it as a probability, it's going to be constrained between 0 and 1. So, okay. So that's all for that one. This one was much shorter than the last one. Hopefully it wasn't too fast, but I don't think it was. But if it was, please let me know. And we'll have a little follow-up maybe in a day or so, because at some point we need to think about what happens when your deviance is a problem, when you have overdispersion of the data. But also we're going to want to think a little carefully. Well, we're going to want to consider other types of generalized linear models. In particular, we'll play a little bit with the Poisson model. So on that, take care of yourselves, and I'll see you soon.